go on.
Okay, so 1 minute papers last time basically some of you want to see what happened. We built the Kleisli category, as it's called, the category of maybe functions in a rather kind of hacked out, just sort of pattern match where we have to sort of a way. And some people want to see that again. And your wish is my command. I was going to do it again anyway, just to get to the essence of what's going on. So I've just, you may have noticed if you have incredible memories that in the previous lecture I'd specialized identity and composition just to the category of sets, and now I've generalized them to work for functors between any categories. I mean, there is an identity functor, and functors are closed under composition, and that's going to be important. But where did we get to last time? We had this notion of natural transformation, which is a polymorphic arrow that doesn't care which object you feed it. It has this important relationship with map, which we call naturality. And in the world of sets that we're used to, it basically says polymorphic functions don't know about elements. So it doesn't matter if you've got some operation that acts only on elements. That's what map does. It leaves everything else intact and just fiddles with the elements. A polymorphic function doesn't know about elements, so it can fiddle with anything except elements. So what we said was, if you've got a polymorphic function, it doesn't matter whether you use map to change all the elements and then do the polymorphic function, or you do the polymorphic function first and change the elements afterwards. And you see, throughout exercise 1, I'm always making you prove stuff like that. So that's naturality, and it shows up all over the place. That's just me checking functor composition. Right. And then I think we finished by checking that yes and join maybe were both natural transformations. So it might be worth looking at just what that cashes out as. We just look at, I should comment that out. At this goal, it says if you've got some function f, well actually, yeah, so what it's saying is if you apply f to an element and then pack it up with yes, that's the same as applying yes to the element and then mapping f across it. That's going to give you yes f of x under both circumstances. So that one's easy. And then it's worth checking out what this goal is to get naturality of join. What have I done? I've commented out the last brace. What was this naturality goal? Well, it says if you've got like 2 layers of maybe, and you want to act on the elements, then you have to use the map function for maybe 2 levels deep to get to the elements, to get under those 2 maybes. And if you do that and then join, it's the same thing as joining and then doing a 1-layer map afterwards. So what we're saying is join doesn't know anything about elements. It just knows about layers of maybe. So then something cool is about to happen, and oh, what have I've lost a lambda. Right. It turns out that in order to build a monad in any category, what you need are these things. So we've got some category, we've got some functor from that category to itself. That's gonna, you can think of that as making a layer, like maybe made a layer of yes or no. And we've got two natural transformations. We've got unit, which says make one layer, start from anywhere, wrap up to make one layer. So that was our yes. And we've got a multiplication which says take a composition of 2m's, 2m layers, and flatten it down to 1. So this was, so you'll see how that, I'm going to put maybe back into this framework in a moment. That's when you'll see it again. And then we need we need 3 laws that tell us something which, I mean, these equations may not look all that intuitive, but let me try and explain it in terms of layers. What unit is supposed to do is to put a dummy layer around something. So what the first law says is if you put a dummy layer around the outside of some lump of if you start with one layer already, and you put a dummy layer around the outside to get 2 layers, and then you do the multiplication to flatten those 2 layers down to 1, because the outer layer you added was a dummy, didn't do anything, nothing changed. So that's basically the same as saying, if you put yes around the outside, and then you join, then all join does is strip off that outer yes. Yeah?
Could you just scroll up a little bit, just I can't remember. Thanks.
Yeah. The second law says if you map unit across something that already has one layer, so that's where you go to each element that's already packed up in a layer, and you put a dummy layer around each of those elements. That's like putting yes on the inside round each packed up element. And then you do the multiplication, you do the join. Then again, that doesn't actually do anything. Another way of thinking about it, it's actually good to, it will be useful for you for exercise 2 to think about this in terms of lists. This time, layers are going to be lists. And what we're saying is, if you make a singleton, if you wrap up a whole list as a singleton list of lists, and then concatenate that down to a list again, you get back where you started. Does that make sense? And if you, let's, maybe I will have a bit of board. I'll just turn this projector off. And gosh, some exciting economics appears, but there's a whiteboard eraser up here.
There's one there. See over on the left.
Aha. So our first law for lists would say if you start with 1, 2, 3, and then you make an extra layer by wrapping it up as a singleton list, and then you concatenate this list of lists, you get back to 1, 2, 3. Yeah? Whereas the other law says if you start with, maybe that's going too low, if you start with 1, 2, 3, and you make a layer around each element to get list of 1, list of 2, list of 3, and then you concatenate this list of lists. You also haven't gone anywhere. The third law says if you have 3 layers and you want to flatten them down to 1, it doesn't matter whether you start by flattening the outer 2 layers and then the 2 remaining, or whether you flatten the inner 2 layers and then the 2 remaining. That'll get you the same answer. So for lists, let's see, we'll need a list of lists. So we'll have list of 1, list of 1, 2, 3, and list of 4. Okay, so if we flatten the inner 2 layers, that'll give us list of 1, 2, 3, and list of 4. So we've still got 2 on the outside. The top level list has 2 elements. We've still got them. And then we flatten again. We'll get 1, 2, 3, 4. Or if we flatten instead the outer 2 layers, we'll have list of 1, list containing 2, 3, list of 4. And then it will flatten down to 1, 2, 3, 4. So it works the same either way. What we're saying is we've got a notion of flattening 2 layers into 1 that lets you flatten multiple layers any way you like. That's all that's going on. Under those circumstances, we can always build a category which is called the Kleisli category after the mathematician, that's somebody's name, Kleisli. So the idea is that you always get an arrow that starts with unwrapped S's and gives you 1 layer wrapping a T. And then...
So, is that the... How does that correspond to the unit thing? Because it seems to me like it's sort of the same thing.
Right, so the unit is the thing we had, that was the thing that we had before, where, yeah, the identity is exactly going to be unit.
Oh, right. Is it,
yeah.
So
this is what we had before, where we said S arrow maybe T. This is the general shape of the thing. Just some arrow from unwrapped S to wrapped up T. And then there better be an identity, which, yeah?
Just as a reminder, what's set F again?
So XF.
XF, sorry.
Yeah, that's the thing that actually unpacks the polymorphic function, or the polymorphic arrow from the natural transformation. Let's just go back to the definition here. So this thing says, you really do get an arrow in the target category between f of x and g of x. So in this case, for unit, the f functor is the identity, so that bit disappears. Yeah, so that's just saying, xf says, give me the operation. Give me the thing that we're actually using. Right. And then, what's the composition? It's the same plumbing we did before. We need to connect 2 of these things together. So we do the first thing, and that wraps a layer, 1 layer around the outside of what it delivers. No matter, we can still map G across that. So that does G to all of the wrapped up things, giving us 2 layers of wrapping. And then we do the multiplication to collapse those 2 layers down to 1, which is what we need at the end. maybe I should do that more slowly. And now, of course, my proofs are going to complain like crazy. But I have to make an arrow from R to wrapped up T's. And I've got an arrow that starts with R, so I start my plumbing. And now I need to get from wrapped up S's to wrapped up T's. And I've got a G that starts with unwrapped S's, so I can map that. And now I've got 2 layers of wrapping around T, and I need to get it down to 1. So that is using the operation from mult. Okay. And then I have to prove the laws. I've done these proofs for you because they're big and tedious, but they get to the essence of the idea in the middle. So what we've basically got to show is, well, what's going on is that as we do operations, each time we do an operation, we're building up layers of stuff. And what we're saying is that we can collapse layers in a sensible way. We can get rid of dummy layers introduced by unit, and we can, and it doesn't matter what order we do mult in to collapse stuff. So the first law says if we do unit and then we do F afterwards to the in a wrapped up way to all of the pieces, then we end up with something that looks like unit followed by map F followed by mult. And the strategy for the proof is to use naturality to get F out of the way. We know how to, because unit is natural, we know how to turn a map after unit into something before unit. We can say, the thing that we're doing on the elements, we can move that out of the way. So we get the F to the front, and that leaves us with something which is just unit then mult. And our first law says that turns into the identity. For the second law is easy because we start with an F, and then we map unit to it, and we just have a law that says this thing collapses to the identity, so that goes away. Composition's really hairy, but in a boring way. We know lots of laws about composition, and we know lots of laws about pushing map through compositions, and we just do all of that systematically. And then we use naturality to get our F and our G and our H all the way to the left. And by the time we get to the middle, we've transformed both ways of doing composition into something that looks like saying, start by doing F, and then use map to do G on the bits, on the elements that come out, and then use double map, so that's giving us something 2 layers deep, and then we can use double map to do H for the elements that come out of that, and that will give us something 3 layers deep. And both ways around start that way. The only way in which they differ is that they then collapse those 3 layers down to 1 by the 2 different strategies. And our law says those 2 different strategies, whether it's outer first or inner first, this is outer first, and this is inner first, they have to agree. So that's the essence of the idea, is that each operation adds a layer when you do it, but flattening the layers after can be done in any order you like. So the point about doing this proof, I generalized it to any category and any functor from an object, any endofunctor as we call them. So that's functors from that category to itself. with two natural transformations that satisfy these three laws, that gives us a monad, and the proof that we get a sensible notion of composable arrow out of that makes no reference to any other structure. It's fully general, and it comes supplied in the library for exercise 2, which means that when you're building monads, you just have to build the moving parts, the things that do the work. So let's just then revisit the maybe construction. I should have actually gotten rid of those things. That's me failing to delete stuff I wrote this morning. Right. Let's see what happens. We're going to instantiate this for maybe, and we use our two natural transformations, unit maybe, which wraps up yes, and mult maybe, which wraps up join. And now we have to prove our three laws. So let's look at them. Right. Unnormalized, we cannot see what is going on. However, if I normalize the goal, I shockingly have to prove that the identity function is the identity function. This is the easy law that we had that we just proved with reful above.
Could you just leave that as an underscore again?
I could leave this as an underscore, but not reful. Okay. Same again, we can't see what's going on, but if we normalize everything, you can see that we're saying, well, if we map yes across x, so that's putting an extra dummy layer around everything, and then we join, that's the same as leaving stuff alone. So there I use extensionality because I'm proving an equation between functions. And now let's see what I'm really being asked to prove. I've got some maybe x, and I'm saying for all the x's inside this maybe x, first of all wrap them up with yes, and then join. So if I pattern match on mx, I should hopefully get two easy subgoals, because that will make the map compute. And here I have to show that yes x is yes, and here I have to show that no is no. So we've shown that if you wrap up the inner elements in an extra yes and then join, you haven't done anything. And then here, I exactly have to show that if you join on, if you've got three layers of maybe, well, I'll do the extensionality bit. Question mark. Here we've got, I should have called that MMMX. Let's do that. Here I've got three layers of maybe, and I have to show that if you join the outer two, and then you join the remaining two, that's the same as joining the inner two, and then joining the remaining two. And again, pattern matching should get us there. So here we just have that the remaining two joins have to agree, and here we get that no is no. So that's the essence of monad. It's some notion of layer, like I said last time, that corresponds to plan to get something. And the unit says, if you have a thing, you can very easily make a plan to get a thing, because you just give the thing back. And the multiplication says, if you have a plan to get a thing, then you can sequence those plans to have a single plan to get a thing. And the laws, yep.
So could you put in mult equals mult unit there?
Sorry?
Could you replace mult with mult unit? Mult equals mult unit.
No, I couldn't, because they're even though the proof looks the same. I mean, it all works by saying, look at what happened in the outer layer. That's enough. But what happens afterwards is different in each case. That's to say, although it looks like it's one of these situations exactly where it's a bit of a pity when you use functional programming as a proof language. What's missing from this picture, from the finished code, is what the goals were. So although we're making basically the same argument, which is to say, do one layer of pattern matching to get a computation unstuck, and after that it's easy, which computation is getting unstuck changes between the two lines. So an important part of what was going on and what we're trying to prove was showing up in the goals, and it's preserved in the video, thank goodness, but annoyingly, it's not in the program text. The way to see what's going on and what's different between these two is to comment this proof out and do it again yourself. And that's how it goes quite often. Anyway, so monad, plan to get a thing. So some notion of plan to get a, where you can turn a plan to get a thing into a plan to get a thing by collapsing two layers. Yeah?
The mult unit and mult, isn't there like something like an induction proof? So the first case works, then you can just assume that the rest works.
That's a very, very intelligent question, and you're about to be proved right when we do our next example. So the question was, is there some kind of induction proof going on where the yes is the base case, and that's what's going to happen. So what I want to do is a more exciting example than maybe, that still gives you a sensible notion of plan to get a thing, where we can see things as happening in layers of computation. So I need to build some apparatus first. I start by building lists, and I show that lists have a map operation, which makes them a functor. That's by the by. I give myself the booleans, which I call 2, because there's 2 of them. You may have noticed that when a type is finite, I like to call it by the number of things in it, just to remind you. I like to use arithmetic operations as type forming operations, like plus for choice and times for pairing, because there really are 4 elements of 2 plus 2. Right, but the thing I actually want to work with is this notion of a bit process. So let's see what a bit process X is. It's a particular kind of plan to get an X. A bit process X. Firstly, if you have an X, you may stop and give back the X that you have. Does this remind you of yes in any way? It's a lot like the yes constructor for maybe. But the other stuff that's going on, apart from just handing back a value, that's where things are going to be different from maybe. Okay? The other thing we're allowed to do is interact by communicating bits. And if you think about it, That's a pretty general notion of interaction as far as computers are concerned. We are allowed to send bits and receive bits. So how do you send a bit? You choose a bit to send, and then you say what process you're going to do afterwards. You still haven't got hold of your X yet, so you're going to need to keep going after you've sent your bit. Then, what about receiving a bit? Well, here, the way I've set things up, you receive a bit, and then you immediately look at it to see whether it was true or false. And you've got two ways to carry on afterwards. I often use the lowercase letter k to abbreviate continuation. I'm not quite sure why I use K for continuation, except that I often use C for constructor. So K is continuation. So this is the continuation after we sent the bit. This is the continuation if we receive true, and this is the continuation if we receive false. So these are sort of tree-like processes where each node either says send this bit and has one subnode, or receive a bit and then split into two possibilities depending on which bit we get. Okay? Well, let's actually program some things up like this. So we should be able to build the process that does nothing other than send a bit, and it gives back a boring value in the unit type. Okay, so let's build that process. We're going to start by sending the bit. And now that we've sent our bit, we need to give back something in the unit type. Well, that's fine. And then we actually have to choose a thing in the unit type, which is very easy. So this is just send the bit, then stop. Yep. So that's that process. This one's slightly, but only slightly more exciting. We have a plan to get a bit, and that's going to consist of receiving the bit and then giving back the bit we receive. So we start by saying receive, and then we have to explain what will we do if we receive true.
Stop with true.
We'll stop with true. And if we receive false, we'll stop with false. Okay, so we've built two very tiny processes. Another thing we ought to be able to do, just to get a firmer intuition for what's going on with these processes, is to run them. So let's see what happens. We have a bit process, and somebody gives us a list of bits that are waiting to be input. We ought to be able to run the bit process on this input, and then let's think about what can happen. Well, it's possible that some bits will be output, so we better give back a list of the bits that get output. And then there's one of two possibilities. Either we run out of bits before we want to stop receiving, in which case we've had it. We get stuck if we want to do a receive and there are no bits waiting for us, we can't make any progress. Or if we're lucky and there are enough bits, we will be able to give back the value we eventually received, we eventually stopped at, and also give back the unused bits, the rest of the input that didn't get consumed by receives. Does that seem like a reasonable way to interpret a process? Let's just do it. So we got our process that's trying to get an X, and we've got our input bits, and we're going to try to figure out what to do. Well, let's look at what the process tells us to do. it tells us to do one of three things. It either tells us to stop, or it tells us to send, or it tells us to receive. Okay? So let's figure out what we should do when we're stopping. If the process says stop, what output does it generate? No output, empty list. Next, we have to say whether the process is going to run to completion. And since it's saying stop, and we didn't run out of inputs, it does run to completion. So we say yes. And finally then, we have to deliver the actual output. That would be the X that we're stopping with. And we have to say what the spare bits are. And that would be all of the bits in the input. Everybody happy with this being how to stop? Give no output, give back the value, give back all the spare bits. Okay. Next up, we have the situation where we want to start by sending, and we know how we're going to carry on after we've done the send. So, how might we proceed?
Split BS.
Well, we could split BS, but that would mean looking at the input, which would be a slightly weird thing to do, given that our process doesn't want to input. Our process wants to output.
So we put the bit in the list that we return?
Yeah, so we're hoping that we get to give back B on the front of the list that we eventually give back. So the thing to do is to see whether we eventually manage to give something back. So let's see what happens. We better actually see what would happen if we ran the rest of the process. So I use with to do that.
Is there any reason to use with over let in that case?
Yes, because I'm going to do some pattern matching in a moment.
Yeah.
Or maybe I'm not. I've got a choice to do pattern matching or not. And in fact, I'm not going to. Let's see what comes back. Okay, back come a pair which consists of definitely the outputs, and if we're lucky, we might get a pair of an X and a list of spare inputs. So we have to give back a list of outputs and say whether we're lucky or not. Fine. We know what the outputs from PX were. So can we say what the outputs from the whole thing is?
Just returns B to it.
Yeah, we stick B on the front. So the outputs from the whole process are B, and then the other outputs from the rest. Okay? And now we've got to deal with whether we succeeded or not, and what to do in that situation. So we've got maybe what happened when we ran the rest, and we need one of those actually. So maybe all we have to do is give back exactly MZ without looking at whether we succeeded or not, because the leftover inputs from the rest of the process, the result from the rest of the process will be the result from the whole thing. And the leftover inputs from the rest of the process will be the leftover inputs from the whole thing. So we can just give that thing back. All we had to do was fix up the output with the extra send. So yes, a let would have done. And having seen that, maybe I'll refactor it. I wonder if I can even do this. It would be nice if it worked. Oh, that's nice. They fixed that. So yeah, you're not allowed, if you can match records on the left-hand side of a let, which is very cool. Okay. So next up, we got to say what to do if we're running a receive. Well, at this point, since we're doing a receive, first of all, we better hope there is an input. Okay. And so in this case, the nil case, we want to receive, but there's no input. So, what's going to happen? Comprehensive failure. On the other hand, if there is a bit, we can look at it to see if it's true or false. And if it's true, we can run the true continuation on the rest of the input. And if it's false, we can run the false continuation on the rest of the input.
Is there any reason to use the name PXT and PXF, well, PX in general, as opposed to just K?
I'm just reminding myself that this is a process that makes X's, which I could do. Well, yeah, K would also have done nicely. I think it chose names very much like that. I think it called them PX and PX1 because the original process was PX. So we've got as far as figuring out how to run these things. So we could even run a tiny process. But if we try running this example, receive 1 on no input, we get no output and it falls over. But if we actually give it the input true, then this time it succeeds, producing no output, giving the value true, and delivering no remaining input. So it did at least eat the input we fed it. However, it would be nice to be able to build up larger processes, not just a single send or a single receive. And the thing that will let us do that is to give bit process the structure of a monad. That's where we head. Okay, so the first thing I do, just crank this out. This is completely boring. Is to give it the structure of a functor. I mean, it's one of those things, you look at the definition of a bit process, you can see that these two constructors give some tree-like structure. They have substructures that are also processes. And then at the leaves of the tree, there are some elements. So do you think that if we have an operation mapping elements to elements, we could do it to a whole tree? All we have to do is traverse the tree to find the elements and do the function wherever we find one. That's going to work. So I saved you the trouble of doing it. I wrote this thing. You can see all it does is go hunting recursively through the tree structure, and when it finds an element at a stop, it does the function. Shock horror. And then proving that that preserves identity and composition is the usual deal. It's just REFL when you reach the base case and rewrite by the induction hypothesis everywhere. You've seen this all before. I mean, it's genuinely annoying to actually have to build this stuff by hand. Perhaps later we'll stop doing that. But for now, we have to build these things by hand. Okay. So I might have to leave, well, I'll get the unit done maybe. To get ourselves a monad, all we have to do is show that round any value we can wrap a dummy layer to make it into a process. And if we have two layers of process, we can flatten them into one. So this says we can turn any value into a process to get a value. And this says if we have a process to get a value, then we have a process to get a value. Okay. Come on. Right. Oh, what the hell happened there? Hit the wrong key. That's what happened. So let's do unit. As ever, we get some ugly looking stuff when we just look at the type, but if we normalize the type, you can see it's saying, is there a way to turn an X into a process returning an X? Why, yes, I think there might be. Just as we said yes for maybe, we can say stop for processes. And then what does naturality ask us to show? It asks us to show something very similar to what we had to show for maybe. And the same proof will apply. I'll get the program written, but I won't get the proof done. But hopefully the program will give the idea. What the hell happened there? Yeah, that's kind of ugly. Maybe I should do this first. Sometimes you get things that are hard to look at until you split them up. We're being asked for something that takes two layers of process and splats them down to one. So I'll just pull that out up top as a helper function. And I call my process ppx because it's a process to get an x. And then what do? I go recursively. In the base case, my input process has stopped handing me a process. But I need to say what process I'm going to use to carry on and get my x. Well, that would be px. So that exactly corresponds to the case where join strips off a yes. And then otherwise, I'm going to go recursively. I can't type today. So that's our join. And I don't have time to do any more of the bits and pieces, but you can see join is an operation which doesn't, because it can't, look at elements, so it's definitely going to be natural. We just have to do some work to convince Agda of that. And just as we did with maybe, we will have to prove some laws. Maybe I can get as far as showing the laws. The first law ends up being, yet again, that the identity is the identity. The second law says, if we take a process and we wrap up all its outputs in a stop to get a process that makes processes, and then join that, that's just the same as the process we started with. And the third law says that if we have a process to make a process to make a process, we can merge those layers down to one single process, either by doing the outer merge first or the inner. So it's the same stuff, and we'll end up with the structure of a monad, and that will tell us how to put processes together for free. We're basically doing the work by explaining how to flatten these layers. Okay, I better stop there. But you get to play this game with lists in exercise 2. And then the reason I'm generalizing to arbitrary categories is that I'm going to get you in a useful way to manufacture a monad that isn't in the category of sets and functions.